What's up, everybody? Welcome to another video. Hope you're ready to flex those brain muscles. This video is an introduction to proof methods. So this is the first of hopefully many videos on proof methods and proof techniques. If you want to see more of that, let me know in the comments. But yeah, since this is the first, I got to cover a lot of stuff and the video is probably going to be long. So I'll make sure to timestamp everything below in the comments as well as the description. Timestamps will be there because the goal of this video is to take a topic that a lot of students feel is very intimidating and confusing and hopefully break it down in a way that helps people understand it better. So if you're taking a course, you can succeed, you can kill your exams. Maybe you're not taking a course, but maybe you still notice some things that you've never thought about before, or that you didn't notice before, right? So that's the main goal of this video. That's why I put the timestamps there, to make it easier for you to get to the information you need. If you only need 2 minutes of information from this video, however long it is, then get that 2 minutes. I'm not offended at all. I just want to make that clear. So I do have two sort of side goals, though, along my main goal, right? One of my first side goals is to show people that proofs are not this daunting, crazy, impossible thing that mathematicians do, right? Because that's the idea I had when I first became a math major. I thought, well, to actually prove stuff, you can't be an undergraduate, right? You have to have a PhD. You have to also be like old, like old and have a beard. That's what I picture when I thought of proofs. PhD, old guy with a beard, all right? And then I got into a proofs course, and it turns out you don't need those things, right? That you can prove things with just basic knowledge of logic and reasoning, as well as some definitions. So hopefully through this video I can show that you don't need a beard either. You can still prove stuff. It's just going to take a little bit of practice, but I think you'll get there quicker than you think if you try, all right? So that's the second goal, and the third sort of goal after that is to even maybe show people that proofs are fun. I mean, I know that's really reaching, but once you get past that initial learning curve, that initial confusion, they do get really fun, in my opinion. It's the ultimate puzzle, the ultimate challenge. You take definitions and you just explore, and you try to go on this journey to reach this result, to showing something is true. So maybe people can recognize that, appreciate it, or maybe you just get the help you need to pass your class. As long as that first goal is accomplished, the other two are and who knows if that'll even happen. But I've already rambled enough. I do have to say two more things, though. First of all, thank you all who voted in my poll. Thank you, guys. Y'all made this video happen, really. I was torn about which video to make on which topic. Y'all said, we want to see proofs. That is so freaking cool. Thank you, guys. And if you didn't vote, no worries. Just go to my channel. Make sure your notifications are turned on, first of all. Make sure you can see my community posts. And just be looking out for that, because I do want to get y'all's input. I want to get y'all's feedback. Yes, I make videos on the topics that I love and enjoy, and I make the videos I want to make, but it adds an extra layer of motivation to know that it's something that y'all want to see. For this video, I am motivated as hell to put something together that I'm proud of and to show y'all and hopefully get a good response from y'all. So I want to keep hearing y'all's feedback, keep leaving that. Last thing I have to say, we're about to get into this video. Last thing I have to say, this video is going to make a lot more sense if you have some basic knowledge of propositional logic, right? So if you know about truth tables, conditional statements, operators, propositions, that kind of stuff, if that sounds familiar and you're good with that, then hope you're ready, hope you're excited. But if not, if you need a refresher, if you want to get caught up, I got two videos up here. And these videos lead into the stuff I'm talking about in this video perfectly. So if you watch those two videos and come back to this, should help clear up a lot of confusion. You should understand this video a lot better. But if you're ready, then let's get into it. What the hell is a proof? What does that mean? All right. And you probably heard that before, maybe just not in a math context, right? Where we usually hear it outside of math is being proven wrong. Maybe you've been proven wrong before. I know I have, right? What does it mean to prove someone wrong? Well, that means they presented some kind of evidence. They formed some kind of argument, and that argument was convincing enough for you to admit that you made a mistake, that you were wrong, right? For you to come to that realization. That's how convincing it had to be. So when we do proofs in math, it's not that far off from that definition, right? We're still forming a convincing argument. We just do it using a sequence of statements. It's very formal. It's very precise. Everything is written out, right? So same general idea, but a little different, okay? A proof is a sequence of logical statements, one implying another. Each leads into the next. That's why when you read proofs, not at this lower level we're about to do, but as you get deeper into it, when you read proofs, they will flow, right? Then, since, therefore, hence, right? You'll see all these cool words we get to throw around, but they should flow if they're written correctly, which together form a convincing argument for why something is true. So that's the goal, is to show something is true. Okay, so how can we prove a statement of this form? This is a conditional statement, so we read this as if P then Q, or P implies Q. How can we prove this is true? Well, we can use the direct proof method, and what we can do is assume the premise is true, all right? And then use definitions, known theorems, so theorems that have been previously proven that we know to be true, and cleverness, don't forget the cleverness, to show Q is true. So statements of this form, we can use this direct proof method. And one of the cool things about this is that statements of this form, there are a lot of very important theorems that are of this form that we use in calculus, right? Mean value theorem, intermediate value theorem, Rolle's theorem, even the fundamental theorem of calculus. We use conditional statements and biconditional statements a lot for the most important theorems. So, and some of them you can even prove directly using this method. So we're learning methods that you can use to prove the stuff you do in calculus. That's pretty cool, just to point that out. But how can we prove this? We assume P is true. We use cleverness to show Q is true. So why does this work? Well, to understand this, we can look at the truth table, and hopefully this looks familiar. If it doesn't, please click that video up there. Hopefully this looks familiar. So when is this conditional statement true? Okay, this conditional statement, if P then Q, is true anytime the premise is false, right? For both these cases, it's true. And it's also true when the premise is true and the conclusion is true. So maybe a better question even could be to ask, where is this false? I know that's a shorter answer to that question, right? This conditional statement is only false when the premise is true and the conclusion is false. So why does this assuming P is true and showing Q is true, how does this work? Well, when we assume P is true, and we write out a sequence of logical statements that all lead to Q being true, that shows that P being true guarantees that Q is true, right? Which means that, the way I think of it at least, is we sort of eliminate this second row from the realm of possibilities, okay? If we show that if P is true, it guarantees that Q is true, then this true-false never happens. It can never happen. So we eliminate that row, and guess what that does? That eliminates the only time when this conditional statement is false, right? So a lot of people get kind of tripped up over the what about when P is false thing, right? But the thing is, both of these are true, so we don't really care about when P is false. We don't have to worry about it. All we have to do is show that P being true guarantees that Q is also true. If we can show that, then we can eliminate this second row, again, from the realm of possibilities. That's how I think of it, at least. And we could therefore say that a conditional statement is true. So this is the direct proof method. We're going to assume the premise is true and use some cleverness to show that the conclusion is true. Hopefully this makes sense. All right, guys, so next I'd like to share some of my own personal tips based on my own experience that may help you when you're trying to prove stuff. So I like to call these Tucci's tips for proving shit. Tucci, that's me. These are tips, and we're going to prove some shit, all right? Pretty straightforward title. So tip number 1, know the definitions. And I'm not sure how to elaborate on this very much. It's pretty straightforward. You just have to know the definitions. How are you going to prove something if you can't even define the things you're working with, the things you're talking about, right? Know the definitions. And guess what happens a lot? It's happened to me a lot, as well as a lot of my classmates. If you know the definitions and you're stuck on a proof, trying to prove something, off to the side you can write out all the definitions of all the things you're dealing with, right? And guess what happens a lot of time? You write out all these definitions and you notice something that helps you finish the proof, that helps you get past that point where you're stuck. Happens a lot with me as well as my classmates. And that kind of ties into the second tip as well. Scratch work is your friend. Don't be afraid to write, all right? That's part of proving, is trying things. If you read a proof that's good and it flows and it's like slick and all that, I can guarantee you that that was not the first draft. That has gone through many revisions, right? That's just part of the process. You have to be willing to write stuff down. It drives me a little bit crazy when I see students say, assume P, and then stare at their paper for 20 minutes. And you ask them, what are you thinking? And they're like, I don't know, I'm stuck. But they're not really stuck because they haven't really tried anything, right? You have to try stuff. Start writing stuff down. At least write down the definitions. Start playing with some algebra, or try stuff. That's part of the process, and that's part of what makes proofs fun. We take these definitions and we explore and we try stuff, and we're confronted with challenges and obstacles and that sort of thing, and we sort of go on this journey toward showing something is true. right? And we get to that destination in our own way, and only we are responsible for our own success of getting there, and we get to experience that gratification, that good feeling, and we've gained all this understanding. Just a beautiful thing, but in order to experience all that, you have to be willing to put pencil to paper, and that means you have to be willing to potentially write something down that's not correct. You have to be willing to be wrong, and that's why I see a lot of students struggle in proofs classes, because it's so ingrained in us. Don't write anything down that's wrong. And a lot of times that's how you learn, especially in a proofs class, is you write something out that's wrong and then you learn from that mistake. So these are my tips. Take them for what they are. These are based on my experience, but hope this helps. All right, guys, we're right about to do some proofs, I promised. But first, I have to follow my own advice. We got to know the definitions, baby. Tip number 1, okay? Know the definitions. So here they are. Here's the definitions we're going to use a lot. These are going to come up a lot throughout your time doing introductory level proofs. Even integers, odd integers, and divisibility. We have to know how to define these, and you probably know what these mean, but maybe you just haven't seen them defined in this way. So let's go through them real quick, and then we'll get to proving some shit. All right, so definition 1, n is an even integer if and only if there exists an integer k such that n equals 2 times k. So if you ask most people what does it mean to be even, they would say that means it's divisible by 2, which is true. But what's also true if a number is divisible by 2 is that you can factor out a 2. And that's exactly what we're saying here, is that if an integer is even, then you can factor out a 2. And if you can factor out a 2, then the integer is even. That's what that if and only if. They imply each other, all right? So hopefully that definition 1 we are good at. You can factor out a 2 from any even number. Hopefully that makes sense, all right? Definition 2, m is an odd integer if and only if there exists an integer k such that m equals 2 times k plus 1. This one's a little less intuitive to understand. The way I think of it is that we are taking the even integers and we are shifting up by 1. And what happens if you add 1 to an even integer? You're always going to land on an odd. And since we can reach or land on any even integer with this 2 times k, that means we can also reach or land on any odd integer by just shifting up 1 and writing 2k plus 1. Hopefully that makes sense. That's the way I think of it, but I don't know, it makes sense to me. All right, definition 3, an integer x is divisible by an integer d if and only if there exists an integer k such that x equals d times k. So this might look like a lot, but think about what we said about even integers. They're divisible by 2, right? So since they're divisible by 2, we can write them as 2 times k. There exists some integer k such that 2 times k. Look, doesn't that line up here? So in this case, our d is 2. So even integers fall under this divisibility definition. It's just a little bit disguised because we're saying they're even, and because there's no d, we're just saying that that d is 2, right? But this divisibility we do use a lot, and it makes sense because if a number is divisible by a number, again, that means you can also factor that number out, right? That means that number that it's divisible by, that d, is a factor of that number, so you can factor it out in front, okay? So hopefully that definition makes sense. And real quick, before we continue to do some proofs, I use a lot of shorthand notation. So for there exists, I use this symbol a lot, this like backwards E. And I'll write there exists an integer k. This is how I'll express that. There exists a k, which is an element of the set of integers, okay? And then I'll write such that as s dot t. I already wrote it there that way. So I use this shorthand notation a lot. There exists an integer k such that. So I don't have to write this full thing out every single time. So I just wanted to show that so you're not shocked when you see this in a lot of my proofs. It will come up. Just a shorthand notation. And you should learn it. It'll save you a lot of time if you can learn this stuff. But let's go ahead and without further ado, let's start proving some shit. All right, guys, now is the moment we've all been waiting for. Here's our first proof. We're going to prove that if n is an even integer, then n squared is an even integer. And this may seem simple, may seem basic. That's because it is. We got to crawl before we can walk, okay? We'll do some harder examples later. First, we're going to build our confidence up a little bit, all right? So how do we start on something like this? Well, it's always a good idea to look at what you're being asked to prove and identify what the hell it is in the first place. Is this a conditional statement? And if it is, what's my P and what's my Q, right? Because we're using direct proof. You know, I need to assume P and then show that that leads to Q. But to do that, I need to know what P and Q is, right? So is this a conditional statement? Yes. If, then, clearly it is, right? My P is n is an even integer. My Q is n squared is an even integer. How am I going to start? I'm going to assume P is true. So assume n is an even integer. And I'm going to try to show that this leads to q. N squared is an even integer, right? Assume n is, can I get away with just writing even? Yeah, probably. That implies that it's an integer based on the definition of even. So assume n is even. Now what? Well, I got a slick definition for even that I just learned. And I'm going to write, then there exists, and I'm going to use this alien hieroglyphic stuff here. There exists an integer k such that, what is true about k? Such that n equals 2 times k, all right? So now we have our definition for even here that we pulled out. Where can we go from here? And if you ever get stuck, a really good idea is to look ahead and remind yourself what you're trying to prove, all right? We're trying to show n squared is an even integer. That means we're trying to show n squared equals 2 times an integer, right? That's our definition for even. We have n here equals 2k. Maybe I can square both sides of this, right? So that's kind of the process, is you try some stuff and then you look ahead again and be like, wait, what am I trying to show again? Because you will forget. When these get more complicated, you'll get lost, all right? So that's always a good idea. Square both sides, then what? Then. And I'm not being very elegant with my wording here, but you can go back and fix it and make it more elegant if you want. Then n squared equals, you need the parentheses here to square it. Don't forget them, a kitten will die. If you don't get that reference, you can click up there. Then n squared equals this 2k, the whole thing squared, which equals 4 times k squared. So now what? I want to show n squared equals 2 times an integer. Well, I can factor out a 2 from this 4 because 4 is divisible by 2. We learned that a little bit earlier. Well, we probably already knew that. We just reminded ourselves of that. So then what? Then n squared equals 2 times 2k squared. Which means what? I have n squared equals 2 times something. I'm done. Wait, I need to make sure this is an integer. K is an integer. That means k squared is an integer. That means 2 times k squared is an integer. This is good. So this is an integer. I'll put a little integer symbol here. I'll mark this integer just to let the world know, hey, I know this is an integer, all right? Well, I'll erase that just in case they think it's integer factorial. I'm stupid. All right, then n squared equals 2 times an integer. Therefore, n squared is even. Therefore, n squared is even. So that's it. Wasn't that fun? Therefore, n squared. All right. And we use this little box deal to show, hey, we killed it. All right. So let's recap, okay? We assumed p was true. We used the definition of even. We did 2 little steps in algebra. And then we said, therefore, n squared is even. That means we showed that if p is true, it guarantees that q is true. Therefore, the proof is done, and the whole conditional statement we have proven to be true. So hopefully this makes sense. We're going to get into a little bit tougher examples as the video goes on, but I'm hoping to do plenty of examples so everybody gets all the help they need. Alright guys, just a quick reminder before we continue. Math is not a spectator sport. If you want to get good at these proofs, you have to actually try them on your own. So I highly encourage and recommend when you get to these points of the video where I show the proof, pause it and try this on your own. Pull out a scratch paper, see what you can come up with, and then press play and compare it to what I come up with. I think that'll help you learn a lot. So let's see if we can prove this. If x is an odd integer, then 3x plus 7 is even. Where do I start? We'll have a conditional statement here. Hopefully we're good at identifying that by now. If then, and my p is x is an odd integer. My q is 3x plus 7 is even. So we're using direct proof method. So I'm going to assume p is true. Assume x is odd. All right, then what do I do from here? Well, now I can use the definition of an odd integer. And that means then what? Then the alien hieroglyphics come back into play. There exists an integer k such that x equals 2k plus 1. Remember that definition? X equals 2k plus 1. All right. Now where do I go from here? Well, let's remind ourselves what we're trying to prove. We're trying to show that 3x plus 7 is even. I have x here. I'm going to multiply this x by 3 and then add 7, right? That's 3x plus 7. Then 3x plus 7, maybe I can get it in terms of k, right? Equals 3 times x, which is 2k plus 1. 3 times 2k plus 1 plus 7, which equals, what does this equal? Let's see, distributive property, so 6k plus 3 plus 7, and then I can combine my like terms. So, let's see, I have 6k plus 10, and that's what 3x plus 7 equals? That's what I'm trying to show is even. How do I do that? 2 times an integer? I think I can factor out a 2 from here. So let's see if that does it. So 3x plus 7 equals 2 times 3k plus 5. What does this do? Is this an integer? Let's see. 3 times an integer, that's an integer. Plus 5. Yeah, this is. So I can do a little integer. Yay, integer. 2 times an integer. That means it's even. Therefore 3x plus 7 is even. Alright. Hopefully that makes sense. Hopefully we follow that. Very similar to the last one. Just a tiny bit different. A little bit more algebra. But yeah, we assumed P was true, used a definition, did some algebra, and arrived at the conclusion that Q is true. Exactly like the last proof, really. Just a little bit different algebra. So hopefully this made sense. Alright guys, here's our next example. We're going to prove that if x and y are odd integers, then x times y is odd. And another way of saying this is that the product of any two odd integers is odd. So how do we prove something like this? Well, let's identify what we're looking at. Conditional statement, clearly, if then. And our premise is x and y are odd integers. Our conclusion is x times y is odd. So we're going to assume the premise. We should be in the good routine of this by now. Direct proof, assume x and y are odd. And then we're probably going to use the definition of an odd integer, right? There's one issue I could see coming up here, though. Is I could see us saying x equals 2k plus 1 and y equals 2k plus 1. But what's the issue with that? What's the problem? That would be assuming that x equals y. And that's not part of what we're supposed to assume. We're just supposed to assume that x and y are odd integers. They could equal each other. They could also not. We can't conclude either way based on this information. We're just assuming they're both odd. So we need two different letters to represent these integers, right? Then there exists a k, but we need another letter too. So then there exists a k and what else? And an m. Both of these are integers such that x equals 2k plus 1. And let's see, I'll have y equals 2m plus 1. Now I have what I need, right? Definitely don't assume extra stuff. That would have been a mistake. I would have been proving something different than this, right? So let's see, then there exists integers k and m such that x equals 2k plus 1 and y equals 2m plus 1. This is true. Now let's remind ourselves of what we're trying to show. X times y is odd. So I want to show that x times y is 2 times an integer plus 1. I have x here and y here. I think I should multiply these together. Then x times y equals what? 2k plus 1 times 2m plus 1, right? And then I can FOIL these out is probably what I'm going to do. So if I FOIL these out, I get, it's a little bit ugly here, 4km, I guess not that bad actually, 4km plus, what do I end up with? 2k plus 2m. See how I got that there? Plus 2m plus 1. Alright, so what do I do now? Let's see. I'm trying to show that x times y is odd. I'm trying to show it as 2 times an integer plus 1. I think I can actually factor out 2's from here. And that's the first thing I noticed is the plus 1 here. So I was feeling like I was on the right track, but since I have 2's in all of these, I think I really am on the right track. I can say this equals 2 times, what would I have left once I take the 2 out? 2km from here. Plus k plus m. And then outside here, I have plus 1. This is an integer, right? 2 times an integer plus 1. That's x times y. So x times y is 2 times an integer plus 1. Therefore, x times y is odd. Therefore, x times y is odd. Hopefully this is making sense by now. Hopefully you're feeling comfortable with this kind of stuff. Alright, next proof. If a and c are odd integers, then a times b minus b times c is even for every integer b. So looking a little different. There's no actual numbers. It's all letters. That scares people sometimes, but it's really not that scary. Let's break it down a little bit. A and c are odd integers. That's our p. That's what we're going to assume. And we're going to try to show that a times b minus b times c is even for every integer b. Every integer b means b needs to stay arbitrary. It needs to stay just a b, right? So let's go ahead and see if we can start. Let's at least start and assume a and c are odd integers and see if we can use the definition of odd somehow. Assume a and c are odd integers. And then we can say what? We can use k and m again. Then there exists integers k and m. Alright, so there exists k and m that are elements of the set of integers such that what? Let's see, a equals k, 2k plus 1. Let's see, and I'll go ahead and go to this line. C equals 2m plus 1. Now what are we trying to show? AB minus BC is even. I have A here and I have C here, and we said we wanted to keep B just in terms of B. So I can just multiply this A by B and this C by B and then do some subtraction. Pretty simple, right? So if I multiply A by B, I'm just going to keep the B out in front for now. Let's see, all right, then AB minus BC equals what? A times B. So yeah, I'll keep the, let's see, I'll keep the A after because I'll keep it in order of A, B, just for organization. 2k plus 1, and I'll write the B out here, minus, and I'll write the B in front here. What's the C? Let's see, 2m plus 1. And I'm trying to show, what am I trying to show? This is even, so 2 times an integer. You know, I noticed there's a B in both, and it may be easier to factor the B out all the way in front. I think that might be easier. So let me see if I can factor the B out all the way in front. Let's see, equals B times what? When I take that out, I'm left with 2k plus 1. And I'm left with minus 2m minus 1, right? The minus has to distribute, minus 2m minus 1. And another way to see this is you can factor the B out straight from here. You have B times A minus C. That's actually, might even be easier to see, right? B times A minus C. This is A, this is C. You subtract, that's exactly what you get. So this equals what? B times, let's see, definitely the 2k minus 2m. The ones actually cancel. The ones cancel. So I have 2k minus 2m. And I think I could actually write this as 2 times an integer because I can factor out the 2 and I can actually put the B back in if I want. So this equals what? 2 times, let's see, if I bring the 2 out and bring the B back in, I have BK minus BM. BK minus BM, which is 2 times an integer. So I think I'm good here. Let's see, AB minus BC equals, and I have this string of equal signs, and I end up with 2 times an integer. That's what I wanted to show. I wanted to show AB minus BC is even. That's exactly what I just did. Therefore, and it's always good to go back and double check. Be like, am I sure I just showed what I think I showed, right? Because sometimes you realize you didn't. Okay, therefore, AB minus BC is even for every integer B. And I'll write for every B belonging to the set of integers. Here we go. All right, I think this is good. Hopefully this makes sense. Let's go back. We assumed the premise. We used the definition of odd integers. Then we did some pretty slick algebra. I mean, some factoring, some different stuff, canceling, distributing, and we ended up with AB minus BC equals 2 times an integer, which means AB minus BC is even, and that's what we concluded with. So, assuming P is true led us to Q is true, therefore the whole conditional statement is true. Alright guys, it's getting late now, it's about 2 a.m. So I think this is the last example I'm going to do, but lots more videos of this stuff to come, make sure to stay tuned. Alright, let A, B, C, and D be integers. If A is divisible by C, we're finally using this divisibility. I showed the definition, I was like, I gotta put one example like this. If A is divisible by C and B is divisible by D, then A times B is divisible by C times D. It's a lot of words, a lot of letters, no numbers. Let's dissect this, see if we can understand it. So these are all integers, again, And this is clearly a conditional statement, if then. But what's our P? Our P is actually this whole statement with the and included. So A is divisible by C and B is divisible by D. So we're assuming that whole thing is true and trying to show that A times B is divisible by C times D. So let's see, proof. I'll write this out here. Assume what? Assume that whole thing. So what does it mean? Well, I'll write it out. Assume A is divisible by what? By C and B is divisible by D. Alright, so we're assuming this whole thing is true. Now we need to use the definition of divisibility. And we could have maybe jumped straight to that. I'm writing out every single step. You could have maybe jumped straight to that. So if A is divisible by C, then what is true about A? Then there exists an integer K such that A equals C times K, right? And same with this B, there exists an integer. So I need two integers. So I'm going to say then there exists integers, and you could write this out in two separate steps. There exists a K such as this, there exists an M such as this, that kind of thing. But I'm going to list them both out here to save space. There exists a K and an M. Both of these are integers, alright? So there exists two of these bad boys such that what? Such that A equals CK, not Calvin Klein, okay? Stupid. Okay, and what else? Let's see. B equals DM. It goes down in the T. I'm an idiot. Alright, so what do I do from here? Let's see. There exists K and M. These are integers, so that A equals CK and B equals DM. What am I trying to show again? I am trying to show that A times B is divisible by C times D. So what does that mean? I'm trying to show that A times B equals C times D times some integer, right? So I'm going to multiply A and B together. Then A and B, then times B equals what? C times K times D times N. Calvin Klein in my DMs. It's so late, y'all. I'm losing it. Okay, what am I doing here? Alright, then AB. I'm trying to show AB is divisible by CD. So I'm trying to show AB equals CD times an integer. Oh, I can make this clear. I can make this real clear. So AB, I mean, it's pretty much there, but I'm trying to show that AB equals C times D times an integer. So I can really just factor out the C times D. And I could say, oh, well, KM is definitely an integer because K and M are both integers. Therefore, and then this is done. Now, that was way easier than I thought. It just sort of really came together in the end like that. So let's see. Therefore, AB is divisible by CD. Alright, and we are done. So hopefully that made sense. AB is divisible. These get a lot more complicated. I'm sorry if these examples were way too easy for you. I wanted to start, you know, very simple, very basic. I'd rather start a little bit behind than start too far ahead and have to like backtrack, you know what I mean? So leaving plenty of room for growth. Hopefully this built everyone's confidence. Everyone feels comfortable, excited, happy, ready to continue this journey of getting better at proofs and that sort of thing. If you enjoyed this video, make sure to hit like. Subscribe to my channel. Stay tuned for more. Leave any comments below. Most importantly, keep flexing those brain muscles. See y'all later.